Hello, everyone. My name is Sergio Botelho from RocketML, and I'd like to talk about the problem of 3D seismic facies classification using distributed deep learning. And this is work done with my colleagues Santi and Vinay from RocketML and Vishal and Pandu from Shell. So just a quick outline of the talk. On the first part, I'm going to focus on just giving a quick overview of the problem of facies classification, show the state of the art, discuss the limitations and challenges of the current approaches. And then on the second part, move on to the more infrastructure part where we look at the application of deep learning methods to solve these problems. In particular, I make the case for the use of distributed deep learning for large 3D seismic facies classification problems, and then show the application of our homegrown solution to this problem, deep fusion, and the results that we obtain on a representative problem. And then finally, discuss future works and next steps. So in a nutshell, the problem of seismic facies classification starts pretty much like any other problem with data collection, which in this business, it's done by means of a source of seismic waves that shoots waves down into the under the ocean, under the subsurface region. These waves then reflect off of the structures there and are picked up by these sensors, these hydrophones that sit on some structure that floats on the water. And by doing this, by putting this data together, one can build this 3D map of the subsurface region, like showing here. Then the typical next step in this workflow is for seismic experts, seismic interpreters, which are usually geology experts, to look at this raw data and map it to what we call label data. So pretty much they identify each point or region in the original volume, in the 3D volume, and associate it with some kind of real geological structure of interest. Like, is this region here a hydrocarbon rock or a water saturated rock, and so on, whatever geological feature that is of interest to the person. Needless to say, that's a very time consuming and labor intensive problem. And depending on the complexity of the data, it might take from days to months to complete. And as such, you'd expect it might suffer from problems of replicability and reliability, right? Two people doing it independently might get to different results. So consistency of results might be an issue here. So that makes this a very good candidate problem to apply some kind of automatic technique like machine learning. And sure enough, for the last several years, people have been doing this, in particular using 2D deep learning, so training 2D neural networks to tackle this problem. This is one paper from a couple of years ago. The issue, though, with this approach of reducing data from 3D to 2D and then training a network is that seismic data is inherently 3D in nature. Okay, so by reducing the data from 3D to 2D, simply because it's very much more expensive to train 3D networks, one might miss geological features that are important. For example, it's easy to see that for a structure like a channel cut, like a trench, right? If you look at the data, if you cut the 3D data perpendicular to the axis of the of the channel cut, you'll be able to resolve it, right? If you're looking along the line of the axis of the trench, you will see it. However, if you rotate the data 90 degrees and do a cut now parallel to the line of to the axis of the trench, you might miss it completely, like shown here. So that shows that seismic data is inherently 3D in nature, and therefore it is good to apply 3D techniques or to train 3D networks to solve these problems. The problem with those is that, like I said, they're much more expensive, much harder, much more compute intensive to train with way more trainable parameters than their 2D counterparts. But nevertheless, in the last couple of years, there have been some attempts to do it in 3D, like this paper from last year, where the authors used a VDG net with a relatively small 3D network with 3 convolutional blocks and obtained a pretty encouraging validation data set accuracy of 82% by training a 3D network there. And they claim to have used these relatively small input patches. So the input to the networks were 32 cubed in size and reported very long compute times compared to typical 2D counterparts. So that's the challenge that we have at hand, the limitation of tackling a 3D problem with 2D networks, and the challenge of using 3D networks because they're much more expensive. So that's what we want to tackle going forward, and not only be able to solve this problem, but solve it fast, right? So going into the second infrastructure part of the talk, uh, I'd like to start by motivating the use of distributed deep learning to tackle not only these problems, but in general, large machine learning, large deep learning problems. We all know that during training, the memory peak during training depends on several parameters of your problem. In particular, they depend on the size of the network, the number of model parameters, the network depth, the mini batch size that you use, and finally, the image dimensionality and size. So for example, here I show a typical result of training 3D segmentation network. In fact, we use a depth 4 UNet 3D. And I show the peak memory as a function of the image size, the linear image size. And as you can see, soon enough, you reach the memory limit of these pretty standard and state-of-the-art GPUs. Like by size 128, you're already above the Tesla RTX 6000 memory capacity. And if you just double the size now, you're above pretty much all the existing GPUs. And GPUs, more so than CPUs, are known to have relatively small available memory, right? So what the kinds of workarounds that people use to, to work around this problem are to reduce the batch size, which might hinder convergence of your network. It might take longer to converge or not converge at all. Shrink the whole network, reduce the number of trainable parameters, which might hinder the precision and the predictability, the generalization of your network. And finally, just give up on 3D and stick with 2D nets, which, like I argued before, it might limit your applicability, the kinds of problems you can apply this to. So our approach is the following. We developed this framework, the software framework that we call Deep Fusion, which it is a fusion of HPC concepts and ideas with machine learning, right? And as such, it leverages these very low-level, tried and true, high-performance HPC libraries like MKL and MPI to maximize performance. At the same time, using hybrid communication paradigms like OpenMP and MPI together to maximize the efficiency of communication, pretty much taking the scalability potential of the system up to the limits of Amdahl's law. And the idea being, without going into too much detail of the design of the software, the idea is it's designed with parallelization in mind, or treating scaling as a first-class citizen. This means that parallelization and distribution are not after the fact ideas that are added on to the software, like it is the case, in fact, in many open source libraries out there, but it is built in from the get-go, built in with parallelization in mind. Just I'd like to mention that we do use, and that's the results that I'm going to show, did use the data parallel strategy, which is this idea of, so you have your data to train, and typically to train on your network, you split the data into mini batches. So in the data parallel strategy, you further split these batches into sub batches, and you dispatch these independently to the workers, which then work on them independently. And then data is gathered out, or reduced out, averaged maybe, by using some communication primitive like MPI or reduce. So in such a way that all the workers at any time have the same copy of the model, and they optimize, therefore, a single, the same objective function. So as an example then of applying this framework to a 3D seismic facies classification problem, we looked at this data set of the Parihaka seismic survey, which is publicly available. It consists of two big volumes, one with raw shockwave data and the other with the labels, the label data. It is of this size here, and it has 6 types of structures of geological features in there, so 6 classes. And we decided to split the data between training and testing by taking 90% of the data for training and 10% for testing. And we did this by taking all the points above x equals some number, 704, to be testing, and anything below 704 to be training, like shown here. So before I show the results, there's a lot of data pre-processing augmentation options that one has when dealing with problems like these. For instance, how do you split your volume into samples, into input samples into the network? Do you take cubes or cuboids? How do you mesh how do you do this splitting? Do you overlap your samples, or do you overlap the cuboids? Do you normalize the data? If so, how, and so on. So we iterated over these hyperparameter, if you will, hyperparameter optimization cycles, and came up with this set of best methods or best techniques to use for data preparation, which was the following. Using cuboids, not cubes, but cuboids elongated along Z, the Z direction, of size 64, 64, 256, or 64, 64, 512. They both worked equally well. And it makes sense that these are elongated along Z because seismic data typically doesn't change much as you walk around X or Y, but it does change a lot along Z. We did find that normalizing the data to -1, between -1 and 1 worked best. And we did find that overlapping these blocks worked better as well. Not only overlapping, but with a level of overlap that increased with depth. So as you go down in Z, they overlap more and more, as shown in this diagram here. That's schematics of how we did the overlap in Z. So with this, we ended up with two data sets. We ran two experiments, and well, the one with 64, 64, 256 samples had about 1,300 training examples and 128 test examples. The other one had about 600 training, 64 test. So for the results, we ran this first about the compute infrastructure. We ran this using Deep Fusion on 16 processes of 4 high capacity HC44 Azure VMs. So these are Azure cloud virtual machines, putting 4 processes per node for a total of 16 processes. The network, the neural network utilized was a depth 4 UNet 3D, which has 13.6 trainable parameters. We concluded that a batch size of 64, we also iterated over these, tried different batch sizes. 64 seemed to work best with a learning rate of the Atom optimizer of 1e minus 4. And here I show the results for the two experiments, for the two data sets. They're essentially the same. They show equally good results. And I show the loss as a function of epoch and both the training and testing data set accuracies. And after a runtime of a little over 4 hours, we reached, or 50 epochs, that's what it took to converge. We reached an accuracy of about 87% on the test data, which is actually pretty on par and even slightly above many of the results out there on 3D seismic facies classification. This with a runtime of only a little bit over 4 hours. So that's pretty encouraging. Here, just a little bit more details on the results. I'm showing for one of the data sets, one of the experiments, the F1 scores and precisions and recalls. And on the confusion matrix here, you can see that most of the classes have a pretty good accuracy, maybe except for 4 and 5, which are the least present classes. There's a class imbalance, and 4 and 5 have way fewer points than the rest. But overall, the results look really competitive. Finally, the last point I wanted to make is, like I said, our software is built with scalability in mind. So here I show an example where we took a much bigger, much deeper network, a depth 7 UNet 3D, which has 1.3 billion parameters, and ran on even bigger clusters on the same Azure infrastructure, right? Going all the way from one node or one node, all the way to 128 processes. And a couple of things to notice here. So the speed up that we obtain is very good. It's almost linear all the way to the end, all the way to 64, 128 processes, showing that our software really scales up pretty much to the limits of Amdahl's law. And so the punchline would be that you can go from 5 hours training time if you use just one process. This is like 300 minutes here, so 5 hours, all the way down to about 5 minutes. So how much you can speed up your training by scaling out with good scalability. So that's all I have time to talk. Just in conclusion, to summarize, we looked at the problem of seismic facies classification in 3D, argued that it's an inherently 3D problem and therefore must be tackled with 3D deep learning. Otherwise, you might miss geological features of importance. We showed our homegrown solution to this problem, which is Deep Fusion, and showed the results of applying Deep Fusion to a typical problem, good encouraging results, and demonstrated excellent, strong scaling of 3D seismic classification problems on a massive network, on a network with 1.3 billion parameters. So in terms of future steps, we want to further tune up the not only hyperparameters, but network parameters and network architecture, and hopefully further increase the accuracy on the test data, and also experiment with different parallelism strategies like model parallelism and higher order optimization methods. So that's what I had. Thanks a lot for watching. I appreciate it, and take care.